So hello dear students. In the last part of the continuous time Fourier series, we have completed some properties, that is time shifting property. So we'll be continuing from that in this part. Okay, we'll be covering the properties of continuous time Fourier series, all the properties, and then we'll be doing some questions on the continuous time Fourier series, some PYQs also. So the last part, the last section, we did the time shifting property, and now we'll use that time shifting property, and now or we will see the application of time shifting property here, that is called half wave symmetry. We have seen even symmetry and odd symmetry in the last part. This is one more symmetry, that is half wave symmetry, and there are two more symmetries, that is hidden odd symmetry and hidden half wave symmetry, that I am going to explain here. Okay, so half wave symmetry. First of all, let me tell you, let us recall the time shifting property. If xt has Fourier series coefficient xk or ck, anything, then x of t minus tau, if we shift the signal by tau, then the exponential Fourier series coefficients will be e to power minus j omega naught k tau. Okay, the effect goes with the same sign, minus tau, so minus tau. Okay, so now let me tell you what is half wave symmetry. Half wave symmetry. So half wave symmetry says that if we have a signal, and we shift the signal by half time period right or left, we shift the signal by half time period by right or left. We shift the signal by half time period right or left. Okay, we have a signal, periodic signal, we shift it by half time period. Time period of signal is t naught, right? We shift the signal by half time period by right or left, and if the shifted signal is equal to minus times the original signal, then the signal has half wave symmetry. Then the signal has half wave symmetry. So equation wise, if we go, then the equation will be if xt minus t naught by 2, that is we have shifted the signal by half time period, and it is equal to minus times of xt, then the signal is half wave symmetry. This is the condition for half wave symmetry. Now, what is the importance of half wave symmetry? That I am going to explain here you right now. First of all, let us see some examples. Okay, so we'll see the examples on this slide. Let me tell you. So we have seen what is half wave symmetry. Now let me tell you what is the importance of half wave symmetry, that what can we actually determine from half wave symmetry. That is we are going to see here. Okay, so applying this property, time shifting property, in the half wave symmetric signal, we can get that k e to power, if I go with the opposite sign, same sign, so it is minus t naught by 2, so it will be minus j omega naught k t naught by 2 is equals to minus ck. Okay, so omega naught t naught, since we know that omega naught is 2 pi by time period, so omega naught t naught will be equal to 2 pi, so this will cancel and it will become e to power minus j 2 pi by 2. 2 pi by 2 means pi k is equals to ck. Now what is e to power j pi? We all know that e to power j pi is minus 1. So this equation will come out to be, if we take ck to the left hand side, so this will become ck 1 plus e to power minus j pi k is equal to 0. Okay, so this is the equation that we'll get. Now if we put k equal to e1 in this, if we put k equal to e1 values, so if we put k equal to e1, then e to power j pi k will be equal to 1. Okay, if we put k even number like 2, 4, 6, 8 and so on, so this term will become 1. So for k even values, this term will become 1. So this will become 1 plus 1, 2. So this result will be 2 times ck will be equal to 0. 2 times ck will be equal to 0. But if we put k equal to negative, sorry, k equal to odd, then k odd means k equal to 1, 3, 5, 7 and so on. So k equal to 1, 3, 5, 7. So this term will become minus 1. E to power j pi, e to power j 3 pi, e to power j 5 pi is minus 1. So 1 minus 1 becomes 0. So 0 equal to 0. That is no information from that thing. Okay. So if we put k equals to odd, then we get 0 equal to 0. Great. So from here, we got two things that I'm going to conclude on the next slide. That is, half-wave symmetry meaning is, if we shift the signal by half time period, then if the signal becomes minus times of the original signal, then the signal has half-wave symmetry. And if the periodic signal has half-wave symmetry, then ck is equals to 0 for k even numbers, and it will be non-zero for k odd. Okay, it will be 0 for k even and it will be non-zero for k odd. So this is a very important property for half-wave symmetry. Okay, so let's see a signal which has half-wave symmetry. Then we'll talk about the hidden half-wave symmetry also. Suppose this is the signal, it is A or minus A. Okay, and this is a signal, periodic signal, the rectangular pulse. Okay, this is 0, this is capital T and so on. So now we can see that this is half time period T naught by 2. If we shift this signal by half time period left, let us say we shift this signal by half time period left, so we will get, if we shift this signal half time period by left, then we will get the signal like this. Okay, here it will be like this. So we can see that this pink and orange are opposite to each other. That is, if we shift the signal by half time period left or right, doesn't matter, so then we will get a signal which will be opposite to this original signal. So we can say that this signal has half wave symmetry. Now one more thing, the signal has half wave symmetry. Now in the last class we studied the even symmetry and odd symmetry. Does this signal has any other symmetry, that is even or odd? Yes, we can see that this has signal odd symmetry. Here it is plus A, here it is minus A. So this signal is half wave symmetric and odd symmetric. Okay, half wave symmetric and odd symmetric. Now from the last class discussion, odd symmetric signals only have only sign terms. Okay, you remember that trigonometric Fourier series has only sign terms. So now since the signal has only sign terms, half wave symmetry says that the signal has only odd harmonics. Signal has only odd harmonics, that is ck is non-zero only for k odd, it is 0 for k even. Okay, so this signal has only odd harmonics, and that too for only that too of only sign, because odd, it is odd signal. Okay, so we can say that the signal has sign terms, and that too odd for sign, only odd harmonics. So these type of questions are asked in GATE exam. So let me tell you, let me take few examples. So this signal is height is 10. Here it is minus 10. Now we can see that this signal does not has any symmetry, because this signal is minus 1 to 4, it is 10, so it does not have any symmetry, even or odd. It is neither even nor odd. Well, first thing. Second thing, does this signal has half wave symmetry? Yes, this signal has half wave symmetry, because we can see that this signal is plus 10 for half duration, minus 10 for half duration. So if we shift the signal, we will get that this signal has half wave symmetry. So this signal has only half wave symmetry. So this signal has only half wave symmetry. This signal has half wave symmetry only, right? Uh, Neither even nor odd. So half wave symmetry means this signal will have odd harmonics. This signal will have only odd harmonics of sine and cos, not the even harmonics. Okay, this signal will have only odd harmonics of sine and cos. Great. What about this signal? Does it have any symmetry? So let us check. We can see that it does not have any even or odd symmetry, because here the triangle is like this and here the triangle is like this. So it does not have any even symmetry or odd symmetry. First thing. Second, does it have half wave symmetry? Let us check. So this is half period of the signal. This is another half of the signal. So if we shift this triangle by half time period towards left, so we will get that this signal will shift, this triangle will shift, and it will become like this. It will become like this. Okay. Now since it will become like this, we can see that this triangle and the above triangle are opposite to each other. So if we shift the signal by half time period, we will get the signal is of minus times of the original one. So the signal has half wave symmetry. Signal has half wave symmetry. The signal has only half wave symmetry. So the signal will have sine and cos odd harmonics. Okay, odd harmonics of sine and cos. Great. Let's move on. This one. So for this, we first of all have to see the hidden half wave symmetry. What is hidden half wave symmetry? Let me tell you. So hidden half wave symmetry. So hidden half wave symmetry means, suppose we have a signal like this. Suppose we have a rectangular pulse like this. Okay. Okay, 0, E naught by 2, E naught, and so on. So here we can see that the signal is capital A value for half period, 0 for next half, then capital A, then 0 for next half. We can see that this signal has neither even nor odd symmetry, first thing. Second, it does not have half wave symmetry, because if we shift the signal by half time period, we will get 0 here. Okay, we are getting 0. Here it is A, here it is 0. So it does not have half wave symmetry, it does not have odd symmetry, neither even nor odd, and it is not half wave symmetric also. We can see that. Great. But this signal has some other symmetry. What is that? If we try to shift the signal on the amplitude axis, shifting on the amplitude axis means we are adding some constant or subtracting some constant. Okay. So if we add some constant or subtract some constant to the signal, so if we shift the signal, on the amplitude axis such that its average value is 0. Right now its average value is not 0, because what is the average value of a signal? Average value of a signal is area over one time period divided by time period. Okay. So average value is area over one period. What is area over one period? Area means the area of this rectangle only, that is A T naught by 2 divided by time period. So we can say that average value is area over a period divided by time period T naught. So here we can see that it is A by 2. This will come out to be A by 2. So we shift the signal such that its DC value or its average value becomes 0. So we shift the signal such that its DC becomes 0. DC means average value becomes 0. Average value will become 0 by subtracting the signal by its average value, or we can say that by shifting the signal downwards by its average value. Shift the signal downwards by its average value. Okay, we shift the signal downwards by its average value. So if we shift the signal downwards, what will happen? So what is the average value? Average value is A by 2. So we shift the signal by A by 2 downwards. Okay, A by 2 downwards. So we will get we shift the signal downwards, we will get something like this. Okay, so we get something like this. So we can see that the signal is capital A by 2 here minus A by 2 here. Okay, A by 2 minus A by 2 and so on. So now we can see we are shifting the signal by A by 2 downwards. So now we can see that this new signal, that is the signal that we have got, will have what are the symmetries that you can see? We can see the odd symmetry also. We can see odd symmetry also. We can see half wave symmetry also. So this signal, the original signal has hidden half wave symmetry and hidden odd symmetry. This original signal has hidden half wave symmetry and hidden odd symmetry also. So hidden odd symmetry and hidden half wave symmetry means the same as half wave symmetry and odd symmetry. Means this original signal will have only sine terms and odd harmonics of sine only. Okay, hidden half wave symmetry, how we will find out? If any signal we are not able to see half wave symmetry, then we can try that we will find out its average value, shift the signal downwards by the average value, and we will check that the new signal that we have got, does it have odd symmetry or half wave symmetry. If the new signal has odd symmetry or half wave symmetry, then the original signal has hidden half wave symmetry and hidden odd symmetry, and thus the original signal will have all the properties of half wave symmetry and odd symmetry. Okay, so this is hidden odd and hidden half wave symmetry. Let's see few examples and then I'll tell you one more concept. Okay, suppose this signal is there. So first of all, let us find out that this signal has any symmetry. Yes, this signal has even symmetry. We can see, okay, we can see that this signal is symmetric about this amplitude axis, okay, this y axis. So this signal is even. But obviously we can see that this signal does not have half wave symmetry, because this is always positive. For half wave symmetry, it is very important that for half time period it has to be positive, for next half time period it has to be negative. Okay, for half wave symmetry it is very important that for half time period it is positive, for next half it is negative, but here it is always positive. So first of all, let us find out the average value. So we can see that the time period is 20. So average value will be, average or DC will be area of the triangle, half base into height. What is the height? Height is 10, divided by time period. So this will come out to be 5. So average value is 5. That is area of the period divided by time period. Now if we shift the signal by half time period downwards, if we shift the signal by half time period downwards, we will get this signal. We will get something like this. We will get a signal like this. Okay. Now we can see that this signal is going from -5 to 5. This is -5. This is 5. Now we can see that if we shift this signal, the new signal, after shifting this original signal 5 by downwards, we'll get this white signal, white dotted lines. So now we can see that for half period it is positive, half period it is negative, and it is also symmetric. Yes. So if we shift the signal, this one, if we shift this signal, this white dotted line signal, if we shift this signal by half time period towards left, then we'll get the signal like this. We'll get a signal like this. If we shift it right, leftwards, then it will get this triangle will come here, and we can see that this triangle and this triangle will be opposite to each other. So the dotted signal that we have got has half wave symmetry. Okay, has half wave symmetry. So even we have already found, so that's okay. So this new signal has half wave symmetry. So we can see that the original signal will have hidden half wave symmetry. The original signal will have hidden half wave symmetry in the original signal. So the signal has even symmetry and hidden half wave symmetry. So we can say that the original signal will have cos terms, and only odd harmonics of cos, will have only odd harmonics of cos. Will have only odd harmonics of cos. Okay, will have only odd harmonics of cos. So this signal, let us find out all the symmetries now. It is very easy for us. So we can see that this is odd. First of all, we can see it is odd. So we can see that this signal is odd. Okay, this signal is odd. First thing. Second thing is This signal, does it have half-wave symmetry? Does it have half-wave symmetry? So let us find out. So this signal, if we shift it by half time period, if we shift this by half time period, then this triangle will go here. So we can see that this triangle and the original light blue triangle, they are not opposite to each other. Okay. So this is not half-wave symmetry. So only odd symmetry is there in this. So odd symmetry means only sign terms will be there. Only sign terms will be there in this whole signal. Okay. Great. Next, this is very simple. Even and half-wave symmetry we have already done. Even and half-wave symmetry. So this signal will have cos odd harmonics. Okay, odd harmonics of cos. Next, this one. So we can see this is neither even nor odd because here it is A, here it is not A, not A. But is this half-wave symmetric? So let us see. So we can see that here it is cos plus A and then this. So if we shift this by half time period back or left side, so we can see that this term will go like this. Okay. So this portion will go left. So we can see that this portion and this portion are opposite to each other, and thus the signal has half-wave symmetry. Neither even nor odd. Half-wave symmetry means odd harmonics only. Odd harmonics of sine and cos. Odd harmonics. Okay, odd harmonics of sine and cos. Great. What about this? So it is very easy to see that this is even and half-wave symmetric. How it is half-wave symmetric? Let us see. So this is the next portion of the signal. If we shift it by half time period backward, we will get it like this. And we can see it is opposite to the original one. So it has even symmetry and half-wave symmetry. So cos odd harmonics. Odd harmonics of cos will be present in this signal only. Okay, this one. We can see that it is neither even nor odd because they are not symmetric nor anti-symmetric. First thing. Second, is it half-wave symmetric? Let us check. So we can see that if we shift this portion by left by half time period, so then we will get something like this. So we can see that they are opposite to each other. The original signal and the shifted one will be opposite to each other. So this is half-wave symmetric, right? Only, neither even nor odd. Only half-wave symmetric, right? Only half-wave symmetric. So these are the properties. Now let me tell you one more very important concept that we'll be using somewhere in the lecture. So one very important point, let me tell you. In the last class we studied, we see how to find out the Fourier series of sine and cos signals. Okay, the signals having sine and cos. Okay, so what about the DC signal? Suppose we have a DC signal. Suppose we have a signal, let us say sine of 2 omega naught t. I'm going to tell you one or two concepts here. So first of all, let us say we have sine of 2 omega naught t. We know how to find out the Fourier series of this. There is no issue in it. We will find out the period. We'll convert the sine into exponentials and then we'll compare and then we'll get the Fourier series that we have seen in the last lecture, right? So great. We have done it, no issues. If we want to find out the Fourier series of this signal, that is we add a DC here. We add a DC here. So we know that whenever we add DC, this term will only affect to find out the Fourier series, we compare each term with k e to power j omega naught kt. Okay. So whenever we compare, then this term, this DC term will give us C0, right? This term will give us C0. This DC term will give us C0 only. So this is the term. So if we compare this, we can get that this DC term will give us C0 only. This DC term will give us C0. C0 is equal to 1. Now, if we add other DC in it, so if we change the DC, for example, I add 2 here. So we can see that if we are adding DC term, then except C0, no other Fourier series will be changing. No other Fourier series coefficient will be changing, right? So if we add DC, then again we can see that only this term will be changing, only C0 will change to 3, rest all the coefficients, rest all the Fourier series coefficients will remain the same. Okay, so what can we say? We can say that whenever we add a DC term to a signal, then only its C0 or the Fourier series coefficient at k equal to 0 will change, rest all the coefficients will remain unchanged. Okay. So, if we add or subtract, DC to a periodic signal, then only C0 will change. C0 will change. Only the coefficient will change at only C0 coefficient will change. Okay. So let me tell you one very important thing here. Suppose we have this signal. Suppose we have this signal. Suppose we have this signal. This is xt, and here it is 7. Here it is minus 3. Okay. This is 0, t naught by 2, t naught, and so on. Okay. So this signal, let us say that xt has Fourier series coefficient xk. Xt has Fourier series coefficient xk. Now we add 3 to this signal. We created a new signal, that is yt. We create a new signal yt, which is equal to xt plus 3. We'll get a signal, we'll get a rectangular pulse. We add 3 here. We'll get rectangular pulses like this. Get rectangular pulses like this. So this is 0, t naught by 2, t naught, and so on. So height is 10 now. Yt plus 3, height will be 10. So here it is minus 3, so it will become 0 there. Okay. So now what I actually want to tell you is, this is yt, that is xt plus 3. So The concept is if the Fourier series coefficient of yt is yk, if the Fourier series coefficient of yt is yk and xt has Fourier series coefficient xk, then xk is equal to yk. All the coefficients of xt and yt are equal, and only this inequality will fail at k equal to 0. So if we find yk, then yk will be equal to xk for all values of k except at k equal to 0. So xk is equal to yk except for k equal to 0. Okay, except for k equal to 0. And how to find out the coefficient x0? So we know that x0 is equal to the average value of the signal, that is the area of the signal over a period divided by time period. So this is your x0. Similarly, y0 is equals to area over the period divided by time period. So this equality is valid for all k except k equal to 0. Great. So let's find out the, first of all, let us draw the signal and find out the Fourier series of this. This is called impulse train. Okay. We can see that we have impulses at 0, we have impulses at 0, we have impulse at 10, we have impulse at 20, we have impulse at minus 10, we have impulse at minus 20, and so on. And area of this impulse is 1, all the impulses. So this is the signal that I have drawn. This is your xt. We can see that this is called this is the impulse train, which is periodic with period 10. Impulse train periodic with period 10. Okay. Now we have to find out the Fourier series of this. Just recall the Fourier series formula. Just recall the Fourier series formula. Okay. What is the formula of Fourier series? Formula of Fourier series is 1 upon time period. Time period is 10 here. 1 upon time period. Integration over time period, so minus 5 to 5. And from minus 5 to 5, we can see that this signal is only equal to delta t. Okay. From minus 5 to 5, this signal is equal to delta t. At dt. Now we know that delta t, this integration, we know that we will simply put t equal to 0 in this whole equation, because delta is coming in the integration. We will simply put t equal to 0 in this whole equation. So when we put t equals to 0, we will get e to power j0, that is 1. So this will come out to be 1 upon 10. So impulse train has Fourier series coefficient equal to 1 upon 10. Okay. Impulse train has Fourier series coefficient that is equals to 1 upon 10. Okay. Now let's come on to the time scaling property. One direct question has came in 2017 from this property, time scaling property. So if xt has Fourier series coefficient xk, then x of at will have Fourier series coefficient xk only. That is, Fourier series coefficient does not change after time scaling. Okay. Fourier series coefficient does not change by time scaling, but if this signal has time period t naught and fundamental frequency omega naught, the x80 will have some changes, because the time period will change by t naught by a and t naught by mod a. Here we are taking a as positive, t naught by a, and frequency, fundamental frequency will become a t naught. Okay, here we are taking a is positive. Okay, so this is time scaling. Remember that the time scaling does not affect the Fourier series coefficients. Okay, it will affect only the time. The time scaling will only affect the time period and the fundamental frequency. it will not affect the Fourier series coefficient values. Okay, so time scaling property, this is enough. Next, conjugation in time domain. Conjugation in time domain means the property says that if xt has Fourier series coefficient xk, then x conjugate t will have Fourier series coefficient x conjugate minus k. Okay, this property is very useful because we have many few properties linked with this property that we are going to see. So xt has Fourier series coefficient xk, then x conjugate t will have Fourier series coefficient x conjugate minus k. So we'll combine these properties, but first of all let me tell you one very important conclusion from this property. One very important conclusion from this property. So what is the conclusion? If xt is a real signal, if xt is a real signal, suppose xt is real. So real signal means any real signal has a property that the signal and its conjugate will be equal to each other, or any real number has a property that conjugate and the number are equal to each other. Okay, xt is equals to x conjugate t. So if signal is real, then it follows this property, and it will also follow ck is equals to c minus k conjugate. And in chapter 1, we have seen one type of signal which follows this property, that is ck is equals to c minus k conjugate. Just remember it. You will get that. Ck is conjugate symmetric. Conjugate symmetric. Okay. So if a time domain signal, periodic signal is real, then Fourier series are conjugate symmetric. Next. If xt is imaginary, so if xt is an imaginary signal, if xt is an imaginary signal, suppose xt is an imaginary signal, then its conjugate will be opposite to each other. Xt will be equals to minus times of x conjugate t. Okay, for example, any number is imaginary, for example 3j. So if we take the conjugate, it will be minus 3j. So the original signal, so the conjugate multiplied by minus times will become the original value. Okay, the conjugate value minus times will become the original value. So if xt is equals to minus times of x conjugate t, means xt is the imaginary signal. Okay, so we can see that here the property will be c minus times of c minus k conjugate, sorry, ck is equals to c minus k conjugate. Okay, c minus k conjugate. Okay, so what is the property? What is the property here? The property is conjugate antisymmetric. I hope you all remember these properties told in chapter 2. So if this is imaginary, this will become conjugate antisymmetric. So if the signal is imaginary, the Fourier series is conjugate antisymmetric. So we have seen 3 to 4 properties now. That is, if the signal is real, then Fourier series is conjugate symmetric. If the signal is imaginary, then Fourier series is conjugate antisymmetric. Okay, and we have also seen the property, that is, if the signal is even, Fourier series is even. If the signal is odd, the Fourier series is also odd. So now let's combine all the properties. Let's combine all the properties of the Fourier series and the signal. Okay, now these properties are valid. Whatever I'm writing here, this will be valid in Fourier transform also. So here we are going to write the type of signal or the property of signal. and the exponential Fourier series coefficient property. What are the properties? If the signal is real, the Fourier series is conjugate symmetric. If the signal is imaginary, it is conjugate antisymmetric. If the signal is even, the Fourier series is even. If the signal is odd, the Fourier series is also odd. Great. Okay. Now, second, signal and Fourier series coefficient. Now, these four properties are like combining these properties. Okay. So, real plus odd. If the signal is real and odd, real and even, signal is imaginary and odd, imaginary and even. So, if the signal is real and odd, so real and odd means odd will give us always odd exponential Fourier series. And whenever odd is there, then it will change the format. So, real will convert into imaginary. Even is there, it will always give even, but even does not change the format. So, real will convert to real only. Odd will give us odd, but it will convert the format, real plus odd. Last, imaginary plus even will give us even, and it will not change the format also. It will not change the format also. So always remember, odd will give us odd but change the format, real will become imaginary. Odd will become odd but it will change the format, imaginary will become real. Okay. So like this you can remember these formulas or these formats or these properties. The last is so what is this last thing? Last thing is if the signal is conjugate symmetric, the Fourier series is real. So if the Fourier series is real, then signal is conjugate symmetric, opposite to these properties. Okay. If the signal is conjugate antisymmetric, the signal exponential Fourier series is imaginary. So these properties are very useful and they are very helpful in solving questions. We will be solving some questions based on these properties. Okay. So I hope these properties are clear to all of you. You have to remember these properties because these properties exactly same chart is followed in continuous time Fourier transform. Same chart is followed in discrete time Fourier series. Same chart is followed in discrete time Fourier transform and DFT, FFT also. Okay. So we have combined all the properties. Great. Now this last one. This property is also very important. This is actually coming from that chart only. Okay. So what is this property? This property says that if xt is a real signal, if xt is a real signal and xt has Fourier series coefficient xk, xt has Fourier series coefficient xk, then even part of xt, you remember even part and odd part of a signal, even part of xt will have Fourier series coefficient equal to real part of xk, real part of xk, and odd part of xt will have Fourier series coefficient that is imaginary part of xk. So you can like put all these properties in the short notes. Okay. So xt is real. So even part will give us real part, even part of xt will have Fourier series real part of xk. Odd part of xt will have imaginary part of xk as a Fourier series. Okay. So these are the properties. Now last is the Parseval's theorem. The last important theorem is Parseval's theorem here. The Parseval's theorem says that xt is periodic signal and periodic signals are बच्चों xt is periodic signal and periodic signals are power signals. So xt is a power signal, right? What will be the power of xt? The power of xt will be equals to 1 upon time period, integration over time period. We know this formula from chapter 1. Okay. The Parseval says that if you want to find out the power of any signal, then power is also equal to summation ck mod square k equal to minus infinity to infinity. This is your power px. So we are writing the power in terms of the Fourier series coefficients. Okay. So the power px is equal to summation k equal to minus infinity to infinity mod of ck whole square. Okay. So this is Parseval's theorem. Now next is differentiation property. First of all, let us see this. Differentiation of a even signal is differentiation of a even signal is odd, and differentiation of odd signal is even. Okay. So how to differentiate a signal? I hope all of you remember how to differentiate a signal. There's nothing new about it, but there's one very important rule. There's one very important rule for differentiation in signals. Okay, what is that rule? We know that if we have a signal that is ut, if we have ut is 0 here, ut is 0, and then again suddenly we have a jump. Suddenly we have a jump at 0. This is a signal which is ut, right? And suddenly we have a jump at 0 location, and jump is of value 1.0, height is 1.0. Sudden jump is there. Now, since there is a sudden jump, if we differentiate this, we have a delta. We know that integration of delta gives us unit step, and unit step differentiation will give us delta. So we can say that whenever in any signal we have a sudden jump, then at that particular location the differentiation will have a delta. I am repeating the statement. That is what the rule is. What is the rule? The rule is if in a signal we have a sudden jump, then differentiation of that signal at that particular location of jump will have a delta. Okay, so here we can see that we have a jump upward. We have a jump upwards. Okay, we have a jump upwards. So differentiation will have a delta upwards. Differentiation will have a delta upwards. Okay. So we will get a delta t at 0. So wherever we have a jump in a signal, we will have a differentiation will have a delta. Always remember that. For example, suppose we have a signal which is like this 0, and suddenly it has a jump. Suddenly it has jump at 2, and jump is the value is -4. Let us say, suppose we have a signal, this is the time axis, and suddenly the signal has jumped downwards by 4, and location is 2. So differentiation of this signal will have a delta, downwards, at 2. Downwards at 2, and what will be the area? Area of delta will be -4. So here the delta will be, we will write delta is -4 delta t minus 2. Why -4? Because we have the signal is having jump downwards of 4 unit. downwards of 4 unit. So this signal will have minus 4 delta t minus 2. Okay, great. So these are the points that we have seen. Okay, so differentiation property. So what is the differentiation property? The differentiation property is says that if xt is periodic with period t naught, if xt is periodic with period t naught, so if xt is periodic with period t naught, then its differentiation will always be periodic. Will always be periodic with same period t naught only. Okay, so if xt is periodic with period t naught, so differentiation will always be periodic with the same period, that is t naught only. Okay, so the property says that if xt is having Fourier series coefficient xk, then differentiation d by dt xt will have the Fourier series coefficient j omega naught k xk. Okay, so this is a differentiation property. So this differentiation property is useful in finding the Fourier series of triangular pulses. Okay, this is useful in finding the Fourier series of triangular pulses. For example, this pulse. Okay, so let me help you in finding out or like applying the differentiation property in this signal. Okay, so this is the triangular pulse. Obviously we can see that it is periodic with period 2 pi. It's periodic with period 2 pi, and obviously triangular pulse, we will always apply the period is 2 pi, we will always apply the differentiation property, always. Okay, so let's first of all differentiate it. So let us say that zk are the exponential Fourier series coefficient of this signal. So xt is having the Fourier series coefficient zk. Okay, now let us differentiate it. Now let me tell you one thing. Are we worried about z0? No, we are not worried about z0. This is the first point that I actually wanted to tell you, that we are not worried about z0, because we can find out z0 very easily from the signal itself, because z0 is simply area of the signal over a period divided by time period. So find out the area over a period divided by time period, that is z0. So we are not worried about z0, we are worried about zk for k not equal to 0. So we are worried about zk for k not equal to 0 only. Okay, so we are not worried about z0. So let us solve it. First of all, its period is 2 pi. And let us find out. First of all, let's differentiate it. So is there any jump? No, I don't think there is any jump. There is no jump, right? There is no jump here. So we can see that this signal, what are the symmetries? Just we can see that this signal has odd symmetry and this has half wave symmetry also. Because triangle is positive, triangle is negative, we will shift it, we will get that they are opposite to each other. So odd and half wave symmetric. But let us differentiate it. So let us say yt is equals to d by dt zt, differentiation of zt. So we can see that from minus pi by 2 to pi by 2, it is going from minus 5 to plus 5. Okay, so it is rising, slope is positive. What is the amount of slope? The change in height is 10, the change in width is pi. So the differentiation will be 10 upon pi, 10 upon pi, 10 upon pi. Okay, height is 10 upon pi. Similarly, we can see that from my pi by 2 to 3 pi by 2, the change is negative, it is going downwards. So height is 10, distance is pi, so the slope will be minus 10 upon pi. Minus 10 upon pi. So this is the signal that we are getting. 10 upon pi minus 10 upon pi, pi minus pi. So for one period we have this signal, for one period, that is enough for us, that is enough for us. This is yt. Now we can find out yk from here, but I just wanted to use that addition property, adding a dc. So let us create one more signal. Let us create one more signal, that is xt, that is xt is equals to yt plus 10 upon pi. Now when we add a dc, we know that it will affect only the coefficient at 0, only the coefficient at 0, no other coefficient will be affected. So since we are not worried about the coefficient at k equal to 0, because we can easily find z0, there is no worries about it. So let us see, we'll add 10 upon pi here, so we will get 20 upon pi, like this. So over a period the signal will be like this. So this height will be 20 upon pi, and this will be minus pi, this will be pi, this will be pi by 2, this will be pi by 2. Okay, so these are the markings. I hope all of you are able to get this. So this is your xt. Now we will find xk. Now we will find the Fourier series coefficient of this signal. From here we can get the Fourier series coefficient of yk, and from yk we can get the Fourier series coefficient of zk. Okay, so we can see that zk is equals to, what is the time period? The time period is 2 pi. The time period is 2 pi. So omega naught will be equal to 1 here. So xk is equals to 1 upon 2 pi, integrating minus pi to pi, e to power minus j, omega naught is 1, kt dt. Okay. Now when we integrate this, we can see that the signal is available only from minus pi by 2 to pi by 2. For rest region it is 0. So 20 upon pi, sorry, e to power minus j kt dt. Great. Now we'll integrate this and we'll get the result. 20 upon 2 pi square. We'll integrate this. We'll take minus jt down. So this signal will be e to power minus j pi by 2 k minus e to power plus j pi by 2 k. Now if we use minus 2j and this term, we can get that it will convert into sine theta. Okay, so minus 2j and this term will convert into sine theta. We'll get 20 upon pi square, minus 20 to minus j k. Okay, so 2 pi, 2 minus 2j, and this term will give us a sine theta, and pi square k will be denominator, sine of pi by 2 k. Okay, so this is your xk. This is your xk. So I hope all of you are able to get this. Great. So we know that xk is equal to yk for k not equal to 0. Okay, except k not equal to 0, except k equal to 0, this condition is valid. Okay, so we can say that yk is also equal to this, except k equal to 0, except k equal to 0, yk is also equal to this only, 20 upon pi square sine of pi by 2 k. Okay, except k equal to 0. We are not worried about k equal to 0. Okay, now from the property we can see that if zt is, from the property we can see that if yt is equals to d by dt of zt, then from the differentiation property we can say that yk will be equals to j omega naught k zk, or we can say that zk is equals to yk upon j omega naught k. Okay, omega naught is equal to 1 because period is 2 pi, so we can see that zk is equals to yk upon jk, yk upon jk. Okay, so we have yk, we'll just put it there, so it will be 20 upon pi square okay, this is this is your zk. Okay, this is your zk. Now this is your zk. Now, since we are not worried about k equal to 0 in this whole analysis, we will find out z0 from the figure itself. Z0 from the figure itself. Sir, Z0 from the figure we can find out the area over a period 0 to 2 pi, we can see the area is 0. So Z0 is 0. Always find out Z0 or any coefficient, any exponential Fourier series coefficient at k equal to 0 from the figure itself. From the figure itself, that is area over a period divided by time period. So we can see that Z0 is equals to 0 and Zk is equals to this. This is the method to find out the Fourier series coefficient of the triangular pulses. Okay, of the triangular pulses. Now, again this signal, we can see that this is a triangular pulse, we have to differentiate it, then only we can find out the Fourier series, otherwise we cannot find the Fourier series. So in Fourier series, we will always apply the differentiation property. So we will differentiate it first. Now, what will be the differentiation? This is your xt, let us say yt. Yt is differentiation of this signal, okay? Okay. Now, I told you wherever there is a jump, we will have a delta in the differentiation signal. So here we can see that in this region, we are going downwards. So we are going downwards. What is the change in height? Change in height is a. Change in width is pi. Okay. So here we can see that the differentiation will be equal to the slope of the line, that is equal to minus a by pi. Here also, and here also. So in all these straight line region, the slope is minus a by pi. The change in height is a and the width is pi. Great. But at these locations, we are going down, but at this location we are jumping up. So there is a discontinuity and we are jumping upwards. By how much? We are jumping upwards by capital A height. We are jumping upwards by capital A height. We are jumping upwards. We are jumping upwards. So we can see that in the differentiation, we will have deltas at 0, pi, 2 pi, minus 2 pi. So we will have deltas and the area of deltas will be capital A. Area of deltas will be capital A. Okay, the area of deltas will be capital A. So differentiation will have an impulse train at 0 to pi, 2 pi, minus pi, and so on. The area of the deltas will be, so this delta will be A delta t. Okay, and not only this delta, the differentiation will also have another thing, that is, in this region we can say that the slope is minus a by pi, here also minus a by pi, here also minus a by pi. So we can see that the differentiation will also have a constant term, that is minus a by pi. Okay, minus a by pi, a constant term will also be there. So we can see that the differentiation yt will have a impulse train, and each impulse will be of height and this will be minus a by pi. Okay, there will be a constant term also there. Okay, so here we can see that yt is equal to this signal. We can neglect the dc part here because dc is neglected everywhere. So yt is equals to this impulse train, and we know that the impulse train has a Fourier series coefficient 1 upon time period. So this is time period is pi, so this is 1 upon pi. So the Fourier series coefficient will be a upon pi. Now using the property yt equals to d by dt of xt, we can see that yk equals to j omega naught k xk, right? So omega naught is equal to 2 because time period is pi. So yk is equals to j2k xk, right? Now, so we can say xk is equals to yk upon 2jk. Now we will put yk is equals to a upon pi. We will get this. Now this condition is valid only for k not equal to 0. Okay. For k equal to 0, we will use the signal again for finding the k equal to 0 coefficient. What is that? So it is equal to the average value of this. Average value means half time period, half multiplied by area upon time period. Area is half base into height multiplied by pi, that is a by 2. So we will get a by 2 here. Okay, we will get a by 2 here, k equal to 0. Okay, now so we can see that these three are the signals. Okay, so x1t, x2t and x3t are the three signals. So we can see the Fourier series coefficient of x1t is 1 upon 2 to power k for k equal to 0 to 100. Okay, so the Fourier series coefficients are real. They are neither even nor odd. Fourier series coefficient real means the time domain signal is conjugate symmetric. First thing. Second thing, this signal, the Fourier series coefficient are cos k pi from minus 100 to 100. Okay, minus 100 to 100 cos k pi. So this is real and even. The Fourier series coefficient is real and even, and since it is real and even, thus the Fourier series coefficient will also be real and even. The third one, the Fourier series coefficient is j sin k pi by 2 from minus 100 to 100. So the Fourier series is real and odd. Sorry, the Fourier series is odd and imaginary. The time domain signal will be real and odd. So you can solve the questions like this. Okay. Now in this question again, here we can see that the Fourier series coefficients are given to us. Okay, Fourier series coefficient is 2 or j 1 by 2 to power mod k, 1 by 2 to power mod k. Okay, so we can see that the Fourier series coefficients are even, so xt will also be even because of mod k, they are even, right? Next, So xt is even, so differentiation will be odd. So third statement is wrong. Now let us check for the real case. For xt to be real, the Fourier series coefficient should be conjugate symmetric. Okay. Now since they should be conjugate symmetric, so we have to check that ck should be equal to c minus k conjugate. So ck is equal to this, right? The minus k conjugate we can find out and we'll get that it is equal to minus j 1 upon 2 mod k. They are not equal to each other. So xt is not real. Xt is not real. Great. Integration property generally is not used. Okay. The only important thing is that if xt is periodic, the integration may or may not be periodic. In case of differentiation, we saw that the differentiation is always periodic, but integration is may or may not be periodic. But the integration is only periodic when the average value of xt is 0. Average value of xt is 0. And this is the property. The property says that xt is having Fourier series coefficient xk, then integration will have xk upon j omega naught k. Okay. This property is not used generally. Linearity property is also not used property. The property says that if x1t and x2t are periodic with same period, then a times of x1t plus b times of x2t gives us the Fourier series, that is a times of x1k plus b times of x2k. Frequency shifting property, this property is also not much used, but the only thing that you have to remember is in case of frequency shifting, the effect goes with the opposite sign. That is, if xt is having Fourier series coefficient xk, then xk minus m effect goes with the opposite sign. So minus m will go with plus m, e to power j omega naught t m xt. Multiplication in time domain, this property is also not useful, but I hope this property might be asked in the format of match the following, so you can remember the formula. x1t and x2t are periodic with period t0, then multiplication in time domain will give us convolution in frequency domain, that is x1k and x2k are two discrete signals. We have to simply convolve the two discrete signals to get the Fourier series of this x1t into x2t. Next, convolution in time domain. Convolution in time domain means we convolve the two signals which are periodic, and they must be periodic. These signals are of same period, that is t0. Okay. Then the Fourier series is t0 x1k x2k. t0 x1k x2k. Multiplication in frequency domain. Okay. So these are all the properties that we have to do. Now let's see few questions. This is EE 2018 problem PYQ. So we can see that from here the signal is odd. We can see that the signal is odd. Okay, we can see that signal is odd. So odd signal does not have any average value. Okay, odd signal has zero average value. Zero average value. So there is no DC term. There is no DC term. An odd signal will have only sine terms. Only sine terms. So B is the correct answer. Only sine terms. And it is not half wave symmetric. It is not half wave symmetric. Okay. It will have all the terms. It will have all the terms. That is B is the answer, not D. Okay. This one. So we can see that this signal, this rectangular pulse, I have drawn this rectangular pulse in this lecture itself. This rectangular pulse is E1 and it is hidden half wave symmetry. Hidden half wave symmetry. Okay, hidden half wave symmetry. Hidden half wave symmetry because if you observe this, if you shift this signal downward, if we shift this signal downward, we will get the signal like this, positive and negative. Okay, and if we shift this signal, we can see that for half period it is positive, half period it is negative. So this will have half wave symmetry. So since it is even and half wave symmetry, it will have cos terms. It will have cos terms. That too odd harmonics. that too odd harmonics. So odd harmonics, cos terms, and an average value. We can see that this signal has non-zero area over a period, so it will have an average value. So this signal will have average value, and the signal will have cos terms, that too odd harmonics only. So sine terms will not be there, Pn will not be there, A0 will be there, and An will be there, that too for n equals to 1, 3, 5 and infinity. So D is a correct answer. Great. Next, this signal, fundamental frequency. Fundamental frequency, we know that we'll simply find out the time period. And fundamental frequency will be equals to 2 pi upon time period. Okay, that is a normal method that we have seen in chapter 1, but there is one more method. The frequency of this signal is 100. The frequency of this signal is 300. The frequency of this signal is 500. Okay, frequency is 100, 300, 500. If you want to find out the fundamental frequency of the signal, we can find out the HCF of this. Okay, HCF of this, and it will come out to be 100. Okay, so omega naught will be 100. Fundamental frequency is 100 radians per second. Okay, otherwise you can follow the conventional method, that is find out the time period. We know the method. We find out T1, T2 and T3. Then we find out the ratios T1 upon T2, T1 upon T3, and then take the LCM of the denominator, and then we find out the LCM multiplied by T1 gives us T0. From there we can find out omega naught. Okay, this question, we can see that omega naught is equal to 2 pi by time period. So here it is given that it is odd, and from here it is given that xt is equals to minus times of x of t minus what is pi by omega naught. We can see that pi by omega naught is t naught by 2. So if we shift the signal by half time period, it is becoming minus times of the original one. So this signal has odd symmetry and half wave symmetry. So odd symmetry means it will not have the DC term. Half wave symmetry means it will have odd terms, odd harmonics only. So this signal will have sine odd harmonics. So an is 0 for all n, bn is 0 for n even. Okay, so an is 0 for all n, yes, and bn is 0 for n even, because sine odd harmonics are present, even harmonics are not there. So this is the correct answer. I hope all of you are able to do it. Great. This was the question in 2017. I was telling you the time scaling property that was asked in GATE exam. So in Fourier series, you can see that mostly property based questions are asked. So it is given that if xt is having Fourier series coefficient ak, then x of 3t, what is the property? The property says that even after time scaling, the Fourier series coefficient does not change. Okay. So what is the first statement? The complex Fourier series coefficient of x of 3t are ak. Yes, this is true. Okay, second, the complex Fourier series coefficient of x of 3t are this? No, wrong. And now, since we are doing time compression, the time period of this signal is 1 second. The time period of this signal will be 1 by 3 second, and omega naught will be 2 pi by time period, that is 6 pi. So from the third statement, we can see that the fundamental frequency of x of 3t is 6 pi. This is true. So 1 and 3 are true. These are correct answer. So these type of problems are asked in GATE exam related to Fourier series. Okay. One more question based on Fourier series. In this question, the Fourier series coefficients are given to us. Okay. The Fourier series coefficients are given to us. Omega naught is given to us pi. Okay. We have to find out the time domain signal. So Fourier series is given to us and we have to find out the signal. We have to use the formula, that is summation n j omega naught nt n equal to minus infinity to infinity. Okay. So we simply have to find out, we have to just apply this. We can see that Cn is present at n equal to 1, n equal to minus 1, n equal to 3, n equal to minus 3. Okay. Cn is present at these 4 locations only. So we can see that this will come out to be C of 1 e to power j omega naught is pi t, C of minus 1 e to power minus pi t, C of 3 e to power j pi t, C of minus 3 e to power minus j 3 pi. So we simply have to put the value C1, C minus 1, C3 and C minus 3. We can see that C3 at 3 location the value is 1, at minus 3 the value is 1, at minus 1 the value is minus j, and at 1 it is j. So we can simply solve the question. C1 is equal to the coefficient of this, that is j. So it is j e to power j pi t. C minus 1 is the coefficient of this, that is minus j. So minus j e to power minus j pi t. C3 and minus 3, at 3 the coefficient is 1, at minus 3 the coefficient is 1. So both are 1. Okay. So now let's combine this. This will combine and become 2 cos of 3 pi t. Okay. And if we combine this by taking j common multiplied divided by 2j. So j common multiplied by 2j divided by 2j, multiplied divided by 2j, and this is, so this will become sin pi t and this will become minus 2. So answer will be minus 2 sin pi t plus 2 cos of 3 pi t. This is the solution of the question. Okay. I hope all of you are able to do it. Great. Now the last is these conditions that are called the Dirichlet conditions. So Dirichlet conditions, Dirichlet says that these are the conditions that you may remember these properties because they can be asked in GATE exam directly. The Dirichlet says that the Fourier series of a signal can be calculated only when ft has finite number of discontinuities over a period, ft has finite number of maximas and minimas over a period, and it is integrable over a period. Integrable over a period. So 3 things you have to remember. If the signal is having finite number of discontinuities over a period, signal has finite number of maximas and minimas, signal has integrable over a period. So these 3 conditions are followed by a signal, then the signal can be converted into Fourier series. Okay. So these are the Fourier series concepts, the properties and all the symmetries. So for GATE exam, you have to remember the symmetries, you have to remember the properties. So questions are asked from the symmetries and properties only, and few things, that is for triangular you have to use the differentiation property and so on. So thank you dear students. Bye bye. Take care.